So now that we've talked about the fundamental theorem of calculus, we now understand that we can find the area underneath the curve using the definite integral of this function. So that is to say, we can say the integral of f of x evaluated from a to b, or integrated, we can say, from a to b, is going to give us this area here underneath this curve in this enclosed region here. So we've already discussed that in previous lessons. So we get that idea. All right, so this is going to give us the area here of underneath f of x here. So I can just actually, let me just write that here. We'll say this. This is going to give us the area under f of x. Now, suppose I had given you a different function. Like on the same set of axes here, suppose we had a different function, and let me just kind of arbitrarily graph something like this. Let's just say that this is g of x. Okay? And so here now, if I wanted to find the area underneath g of x, I could go ahead and just shade in the same region under the same interval. So let me just go ahead and shade this in. It's not going to be super precise here, but you get the idea. So if I said, now if I integrated from a to b for this function g of x, I'm going to get now the area underneath g of x. Okay? We're just doing kind of the same thing with a different function now. Now, suppose I then asked you to find this area. The area, well, let me actually use a different color here. I'm having a hard time selecting which color. Let's do something a little different here. Let's just go ahead and just do, I don't know. Why am I taking so long to think of this? All right. Let's say I just said I wanted to find this area here. The area that is in between, the area that is in between f of x and g of x. Well, it would then make sense that if I take the green region that I had highlighted earlier and I subtract the area of that purple region, what's left over is this area that I'm kind of delineating here in blue, right? This region here would be what would be left over. So in other words, I could subtract these two integrals. And this will then give us, let me kind of zoom out here, this is then going to give us the area enclosed between f of x and g of x. And using our integration properties, we can actually write this statement here a little bit more simply. We know that this is also then equivalent to f of x minus g of x here, dx. Okay? So this is going to give us, this is the same thing. Integrating each one of these terms individually is the same as subtracting these two functions and integrating that result. And so the idea here is not necessarily that it's always going to be f of x, but really thinking about what we consider whatever is our higher function, or the larger function, if you will, however you want to kind of conceptualize that. The idea that if you take the higher function, the one that has more area, and subtract from that the lower function, or the quote-unquote smaller function, right, then you are going to get whatever region is enclosed between them. So that's the main idea here of finding the area between curves, and that makes a lot of sense. We're just subtracting the lower region, if you will, or the lower area. And this also applies if we were to find this integral with respect to y. So if I had another function here, for example, and this time I've got a function, let's just say that looks something like this, and we said this is a function as f of y. And let's draw maybe a function that looks, I don't know, something like this here. We said that this was g of y. Let me go ahead and finish this up here. And I wanted to find the area between these two regions here. And notice that these are both functions of y, not of x. So what does that mean? It means that this partition here, we will be integrating from negative to positive going up this way. We're actually integrating up towards this way. So if this were our, let's just call this here our a value down here, and this is our b value down here. In this case, this time, we would say we're going to integrate from a to b, and we want to kind of think about this function as almost taking this and rotating, if you will, if that helps you kind of see from that perspective. So if that's the case, what is our higher function here? It's equivalent to whatever is our right function. So we can say that f of y here, this is our right function, or our higher, and let's just change colors here so we can see this. And then g of y here, this is our lower function, or quote unquote, or in this case, our left function. So we would think about this as our right minus left, if that helps at all. And again, if it helps at all, you can kind of turn your head and see this, but this idea that we're seeing still the top minus the bottom here, and that hopefully will make more sense because now we're thinking of it in terms of x. And the only thing that we just need to be a little careful about is remembering that we're integrating from the negative to the positive. So we're going to be integrating up the y-axis this way. So in this case, we would write f of y minus g of y dy. So this is how we would integrate something if this were a function of y. So I'll do an example of that in a bit. So with that said, let's try some practice problems. And before I proceed, I'm going to encourage you right now to pause the video, get your graphing calculators in case you haven't already done so, because we're going to need them for some of these intersection points and some of these bounds. Okay. So let's start with this first one here. Go ahead and plug these two functions into your graphing calculator and sketch the curve. So if you had a chance to do that, hopefully you found, and this one's a little bit tricky because these two functions actually intersect at two different points. And if you just kind of went with the default window that your graph provided, you would see here that this is g of x here. This is g of x. And let me actually graph f of x in red here. So f of x would actually look something like this. Let me go ahead and graph that. Okay, so f of x actually looks something like this would be f of x here. So what we see that these two functions actually are going to intersect at three different points. I think I may have mistakenly said two earlier. So what we're going to see is this region here and this region here. So those are the two areas that we want to find, and we want to add them up. So let's start with the first one. Let me kind of zoom in on this first one here. So we know that we are integrating from left to right here. So what I care about then is where am I going to be integrating from? Where is my starting region? Or where does my region enclosed region start? Well, there are two ways to do this. We can use our graphing calculators. What we could also do is actually, let me take a step back. What we could also do is we can find our intersection points algebraically. That is, to find the points where two functions intersect, we would set them equal to each other. Now, for the sake of time, I'm okay with you just going ahead and finding those intersection points in your calculator. But just know that we would be able to find them this way by just setting these equal to each other as well. If I can kind of show you these two graphs, let me kind of zoom out of this here. So hopefully you found something like this here. And so you see that this graph, these two graphs intersect at negative 1.699 and also here at 0, 0. So those are the two bounds that we're going to use for my intersection. So let me go back to my notes. And so negative 1.699 and this here being x is equal to 0. Those are where my graphs are intersecting. So my first integral I'm going to set up, and let me actually just indicate that I'm doing this one, is going to be from negative 1.699, and this is the 0. And think here, what is my quote-unquote higher function, if you will? My higher function is f of x. And then my lower function is g of x. And that's going to give us the area enclosed in that first region there. So you can go ahead and evaluate this into your calculator, and you should hopefully find that it's about, this is about 3.716. Okay, now let's do the second one. And I'm just going to move this intersection to the sides just so we know algebraically how we could find those points. So now let's find the second one here. Now for the second one, let's do this in, let's say, green. We're going to be integrating now here, this enclosed region. Well, again, we want to refer back to our graph. And in your graphing calculator, you can use the intersection points. But hopefully we see that these two graphs are going to intersect again at 0, 0. And then again, up here at 3.696, if I can show that. So this value here is going to be x is equal to 3.6, did I say 696? 699, there we go. All right, so now that we have that, let's go ahead and set up the second integral. We're going to integrate from 0 to 3.699. And this is, this time, our higher function, if you will, is going to be f of x, or g of x, I should say, g of x, and then we're subtracting from this the lower function f of x. And I can move this graph all over to the side. And this is going to come out to be approximately 29.923. So we're going to add these up. And when we do that, we get approximately 33.639 units squared as our total approximated area that's enclosed between these two. So the main things to be careful about as we're doing these problems is to know algebraically how to find intersection points, and then also how to do those graphically using the intersect feature, as well as being careful to know what is the function that we are subtracting, what is the lower function, if you will. Okay? All right. Let's do an example of a function that or a problem where I would expect you to be able to do this without a graphing calculator. So let's try this next problem here. Let's find the area of one region between y equals cosine x and sine x. So let's try this one. So this is a function that's pretty easy to graph. We can just do something like this. So we know if this is pi, and this is 2 pi, this is 1, this is negative 1, this would be pi over 2, 3 pi over 2. Okay, so let's go ahead and graph cosine x in blue. So cosine x would look something like this. I know my critical points here for cosine, and this is just a sketch, just so we can visibly see which is the quote-unquote higher function and lower function. Sine x would then look something like this. So this is going to look something like this. And this is not a great graph, but just to kind of give you a sense. So now, what we care about are these intersection points. Where are my two functions intersecting? And instead of guessing, we can find these algebraically. We can set cosine of x equal to sine x. So where are the first two places where these functions are intersecting with each other? And if you know your trigonometry, then you should hopefully know that they occur at pi over 4 and at 5 pi over 4. Those angles give us the same outputs, or the same y values. So this is at pi over 4, and this is at 5 pi over 4. Okay? So now I can integrate by finding this area's region, or this region's area, excuse me, as we integrate now from pi over 4 to 5 pi over 4. And in this case, we see that sine of x is going to be the function that is the quote-unquote larger function. So it's a sine of x, and then minus our blue function, cosine of x, and all of that with respect to x. Okay? And this is a pretty easy function to integrate. This is going to give us negative cosine x minus sine x, evaluated from pi over 4 to 5 pi over 4. So let's just evaluate these functions. Cosine of 5 pi over 4 is negative root 2 over 2, but since we have a negative in front of it, that's just going to be positive root 2 over 2. Sine of 5 pi over 4 is also negative root 2 over 2, but again, since we're subtracting it, we're going to be adding root 2 over 2. Now let's evaluate this at the lower bound, which was pi over 4. So cosine of pi over 4 is root 2 over 2 with a negative in front, so negative root 2 over 2. And sine of pi over 4 is also root 2 over 2, which we can simplify this easily as this is all just root 2. This is going to be adding root 2. So our final area would be 2 root 2 units squared. That would be our region there. Okay? And finally, let's do a problem now where we will be integrating with respect to y. So let's take a look at these functions here. Okay? Let me just kind of zoom in on this. All right. And let me get this out of the way because that's going to kind of bother me. Let's put this all the way over here. Okay? All right. All right. Okay, so let's come back to this. All right. So what would this function look like? Well, if you wanted to, you could rewrite these functions in terms of x. For example, we see that this is x is equal to y plus 1. You could write this as y is equal to x minus 1. Although these are pretty simple that you could probably do without having to do that. 3 minus y squared, hopefully we see that this is just kind of a sideways looking parabola, if you will. with a x-intercept at 3. And so if it's a negative y squared, then your graph should look something like this. And you can just plug in points too if you want to check. All right, this would be -1. Okay. G of y looks like y plus 1, which we said is equivalent to x graphing x minus 1 if we wrote it as a function of x. So, or you could just plug in points when y is equal to 0, x is equal to 1. When y is equal to 1, x is equal to 2. So you see that your graph is going to look something like this. So now we see that where these graphs are intersecting, we see it's this region that we want to find the area for. And let me write these coordinates. This point is going to be -1, -2. And this point here is going to be 2, 1. And again, if you wanted to find your intersection points, you could set these two functions equal to each other and solve. Right? This would be not too bad to do. This would be 0 is equal to y squared plus y minus 2. Right? Y plus 2, y minus 1. So our y intersection values, y is equal to -2 and 1. So we see that. So for our integral then, we are going to be integrating from negative to positive. That is to say, these rectangles that we're adding up are being integrated in this order from negative to positive. So our lower bound, we would choose -2 all the way up to +1. Remember, we're integrating with respect to y, so we're going vertically up that y-axis. Now, same kind of way that I modeled this earlier, if I needed to show you this, if this helps at all, ask yourself, what is the quote-unquote higher function? Well, it's 3 minus y squared. So if we look at it from this perspective, our right function would be 3 minus y squared, or f of y. And we're subtracting from that g of y, which is y plus 1. All of that with respect to y. Okay? So this, again, simplifies to this. And that's pretty easy to integrate. That's going to give us -y cubed over 3 minus y squared over 2 plus 2y. All of that evaluated from -2 to 1. And for the sake of time, we'll say that this is just 9 over 2, or 4/5. Okay? So, again, just to reiterate, the key thing as we're doing these, whether or not we're integrating with respect to x or y, is to identify the intersection points, either using your calculator or algebraically, and just be very clear about what is our quote-unquote larger function or higher function, and which one is our smaller or lower function.